This is going to be the last video, last set of video in the series, where we'll be considering the last topic in variation, which is the last type of variation, of course, the partial variation. I welcome you back to the channel. If it's the first time, I will enjoy you to subscribe to the channel because we post contents that help you to understand both mathematics and science by bringing it to you as simple as possible. Alright, today we are going to be considering partial variation. If you remember vividly in our previous videos, if you have not watched them, I will enjoy you to also go and see those videos. We discussed about the first three types of variation, which are the direct variation, the indirect or inverse variation, indirect or inverse variation. And we also have the joint variation. Alright, then the fourth one is the partial variation. This partial variation has a number of uniqueness, a number of peculiarities with it, and we're going to actually talk about them now. You see, direct variation is the one where there is one variable that is dependent and the other variable that is independent. So the dependent variable is of course dependent on the independent variable for its value. So for example, the amount of the quantity of milk you will get in the store is dependent on the price that you're willing to pay. So your price is the independent variable, but the quantity is the dependent variable. So your quantity depends on the price. So, and actually you can place them, interchange them. They can be interchanged. So my point is that in your direct variation, it is such that the change that occurs to one of the variables directly impacts the other variable. That is, and I mean, they are going to have the same kind of change. So for example, such that if let's consider the variable y and x, for example. If variable y increases, it is imperative that the variable x also increases. So that is the idea of direct variation. Hence, the reason why we write it in this notation, we say y is directly proportional to x. And when we introduce our constants, which is, I explained that the constant is the actual reason for the relationship to exist. So we now have that y will be equal to kx. Notice that our constant here is just k. So this is the notation for direct variation. And of course, graphically, what you are going to have is this way. Since we are plotting a graph of y against x, you're going to see that since the variables are going to experience the same kind of change, so that if y increases, x increases, you're going to have a linear graph that is progressive. Alright. So in the same way, if x decreases, y also decreases. Alright. Then the indirect variation. Indirect variation is such one that the variables also depend totally on each other, but a reverse relationship exists between them, such that an increase in one will lead to a decrease in the other. So for example, you remember when you were little, that you play on the seesaw, that if one person sat here, the other person sat here, once this person went up, this person must surely go down. So that is the kind of relationship that exists here in the indirect variation. So we have this notation that we say y, if I consider variable y and x again, so y will be inversely proportional to x. So this is inverse proportionality. Of course, you see we are writing the reciprocal of x, not just x now. So the notation is going to be y equal to k over x by introduction of k. Now it will be k times 1 over x, of course, and it will be k over x. So this is the notation. And of course, the graph is going to be like this. We have y and x there. Because it is a reverse relationship, what you're going to find is that as y decreased, x will increase, and vice versa. So you're going to have something like this, a regressive graph. So the graph is regressive instead of progressive. So you can see that although x value here is increasing as you tend to the right, but the y value is actually decreasing. So this is an indirect variation. Now coming to the joint variation. In the joint variation, we obviously know that the relationship will be between more than two variables. So you can have any form of graph. You can have linear, and of course you can have linear progressive and linear regressive occur on the same graph. So for example, if I have y is directly proportional to x, and of course the same y is still directly proportional to z, so you're going to have something like this. Y will be equal to kxz. Why? Because the x is directly, y is directly dependent on x, and as well directly dependent on z. So you're going to have this kind of relationship. And the graph is also going to be progressive because it is totally direct relationship here. Now, but if it's something like y equals y is directly proportional to x and y is inversely proportional to z, you're going to see that you're going to have y will be, when you introduce your constant, you're going to have y equal to kx over z. So in this kind of situation, you're going to have two types of graph. You're going to have a progressive with respect to x and a regressive with respect to z. Alright, but let's come to the partial variation now. In partial variation, let's still use variable y, which is the dependent variable, is not totally dependent on either of the two. We usually use two other variables aside the dependent variable. So we have two independent variables, one dependent variable. So that dependent variable y is not always totally dependent on either of both variables, as the case is in joint variation, such that y is totally dependent on x and totally dependent on z at the same time. But in the partial variation, y is only partially dependent on x, and will partially dependent on z. So our notation is going to be like this, that y will be, let's say it was in direct relationship with x. You're going to have y is partly directly related to x, partly, and y is directly, let's say it's still a direct relationship with z. It's going to be y is partly directly related to z. So when you are going to be adding a constant here, because y is not directly related to both of them, you are going to introduce two different constants, because the two different constants drive these equations. So you're going to have something like y equal to, let me introduce constant. You can use arbitrary letters. I want to use a and b for this example. So you're going to have y will be equal to ax plus bz. So this is going to be the equation we are going to work with. So you see that the value of z does not totally affect y, or we would say it doesn't cause a significant change on y. Of course, y is going to change a little, but it's not as significant as when both values of y, x, and z changes. I hope that is clear. Okay, so, and the graph of the relationship or partial variation, of course, is going to be like this, because it's not going to begin from origin, because the value of one variable might have a value and the other will not have at a particular instance. So, the variable might be 0 at one point, the other variable will have a significant value, another one have a negative value. So that's why the graph is always like this, not usually from origin. Okay. So now let's also talk about the way we now write the different notations we can have in partial variation. So for example, we could have something like this. We could have if y is partly constant. So when you hear something like if y is partly constant, constants in mathematics are simply numbers. Just when a number exists without an algebra beside it, then that number is said to be constant. So when you say y is partly constant, it means that y is partly a particular number. So let's say the number was actually 1. So it means that y is partly a particular number. So if it's partly a particular number, of course we must introduce our constants. So it will be y equal to a times 1, which is y equal to a. So, but for example, since it says y is just partly constant, it means that y will be equal to our constant without any number, of course, without any other value outside. This is different from when you say y is partly directly related to x, or partly inversely related to x. Alright, so if it further says y is then partly related to the square of z, or the square root of z, you have something like this. So when you're going to write your full equation, you're going to have y equal to a, because it's partly constant, and our second constant is b, because we're using a and b as our constant. So you're going to have plus b root z, and this is going to be the equation you're going to work with. Alright, having understand that, let's use that in solving a particular question. Alright, we'll be attempting this question. And as you well know, the first step to take in addressing this question is to do it step by step, using, I usually call it the heuristic method. Write the parameters that you are given step by step. Interpret the question step by step, and you're going to get it. Alright, so let's do this. We have y is partly constant. As we earlier explained, we are going to equate y to a constant. So say for example in this question, I want to still use a and b as my constants, taking a and b as constants. So we are going to interpret the question. It says y is partly constant, so that y will be equal to my first constant a, and partly varies as x. So you don't need to be told it's direct variation. I'll explain that in direct variation. Since it just says partly varies as x, so you know that that is direct variation. So it also partly varies as x. Partly varies as x. So this will be, you now interpret all of it to be equal to, so therefore y will be equal to a plus bx. So now you can introduce your constant to this place here. So this is the equation with which you will be working. This will be the equation, the grand equation that will be driving all of the, that will help us to solve the question. So one thing about this partial variation is that you almost always end up with a simultaneous equation. And you're going to see an example here. So let's continue interpreting the question. It's now saying that y. So having gotten this, we can now go on to fixing our values. You say y, if y equal to 45, so we now plug in y. You see, that is why it is essential to first get the grand equation. So we now fix y, which is 45 in the first place, is equal to a plus x, which is 10, b into brackets 10. So our aim is to actually get what these constants are. So we're going to have 45 equal to a plus 10b, and this becomes our equation 1. Then we'll go further. It says, and y equals 87. So we can separate that and say y equals to 87. Y is 87. So we plug in 87 equal to a plus b into bracket, and when x is 24. So we can go further and say that 87 is equal to a plus 24b, and this becomes equation 2. Alright, let me write our two equations here. So we have 45 equal to a plus 10b, which is equation 1, and 87 equal to a plus 24b, equation 2. Alright, we can use the simultaneous equation. There are two basic methods, and there are many other methods, of course, but we're going to be using elimination method here since it's faster. So we eliminate this. If you have seen my series on simultaneous equation, you would understand what I'm doing here. You eliminate this. We're going to be using, because they have the same sign, we're going to be using minus to eliminate. So it means I will subtract this equation from this equation and this equation from this equation. So when we subtract this from this, we're going to get this minus this 2, this minus this 4. So we have 42, negative 42, of course, minus 42 is equal to 10 minus this, that is minus 14b. So here we can now divide through by minus 14. So here we now have minus 42 equals minus 14b. The Bible says minus 14, as we have written here. So we have negative, take care of negative. We have here 1, here 3. So B represents 3. So we've gotten our first constant. So we can now go further to plug in the value of that first constant into the equation so that we can get the second constant. So we can plug it into equation 1. Since equation 1 says, so we can say substitute that 3 for B in equation, we can use equation 1. So we have 45 equals A plus 10B. This is our equation 1. You can label it again. And we're going to be substituting 3 into the equation in place of B. So anywhere we find B, we put 3. That's what it means. So we have 45 equals A plus 10 into bracket 3. So we now have 45 will be equal to A plus 10 by 3 is 30. So we have 30 here. And then we, bring this one, collect like terms. So we have A will be equal to 45 minus 30. So A will be equal to 15. And that is the value of our second constant. So we have done the first step. We have done the first step in the equation, but we have not even answered the first question. The first question asks us to find the equation connecting y and x, as we usually do. Since we have gotten the value of constant, it's after you've gotten the value of constant that you can now write the equation connecting them. Alright, so the equation connecting them is going to stem from this, because this is the grand equation. So it's going to be y, so A, which is the first question, y equal to, A now is 15, so we're going to write 15 plus B, we got it to be 3x. So this is the equation that connects y and x. So we have answered question A. Now let's answer question B. So notice, you have to first find the constant using all of these processes to find the constant before you are able to answer the equation, get the equation, determine the equation connecting the variables. So you have the second question. It says find y when x is 18. So according to this equation, it says you find y when x is 18. So y is unknown now, but x is known to be 18. So of course what we're going to have is y equals to 15 plus 3 open bracket 18. So because our equation is 3x, so we're going to just plug in the value of x now, which is 18, into that equation. So we have y equal to 15 plus 3 by 18. That is 54. So we're going to add this, and we have y will be equal to this plus this. That will be 69. And that is how to solve that question. All right.